problem. Wait, we're done. That continues the lesson about zeros of polynomial, but we are doing lesson 3 entitled Zeros of Polynomials. Well, we've already been looking at zeros, but there's so much more to it than just, oh, here it is on the graph. It's where it crosses the wonderful x-axis. So I have this beautiful polynomial, and I can say to myself, well, I have a real zero here, I have a real zero here, I have a real zero here, and one here, and probably one over here. That looks like it goes down forever, and that goes up. So those are my real zeros. There could also be complex zeros that don't show up on the graph. Okay, I just so happened to see, Aaron, I don't know what you mean. Why, sir? Why what? Why are these real zeros? You can talk.
Talking about the chat, sir.
What in the chat? You chatted. I just saw yours come up. I don't usually stare at my computer, but I was at that angle. I saw yours come up. You said why? You're replying to somebody else's chat?
No, I'm replying to yours because you sent me a message.
Who sent you a message?
You did. It says you did.
No, I didn't send no message.
Oh, okay. Sorry.
Well, you know, I think, did I send a private to one person, but I thought it was, maybe I sent it to the wrong person. I can't remember what the question was. I guess I better look. Oh, yeah, it went to the wrong person. Let me fix it.
Okay, thanks.
So it wasn't you. Okay, let me type this in. Did it while. Okay, I sent it to the right person. It's very small on my computer, so sorry to bother you. Mystery solved. Okay, we're going to learn some theorems today, and one's called the Factor Theorem, one's called the Rational Zeros Theorem, one's called the Conjugate Zeros Theorem, and then Descartes Rule of Sign is actually kind of a theorem, but it's not really a theorem. It's just a rule that Rene Descartes came up with. And so let's start with the Factor Theorem. I don't think I'm going to get this all finished because some of these problems take a long time. This may be a 2-dayer. For any polynomial f of x equals f of x, that's just any polynomial like this one right here, f of x, x minus k is a factor of the polynomial. What that means is, I didn't mean to move that thing over. If I cross the axis here at some zero, and I call it k could be a 5 for that matter. And we talked about that if I did synthetic division on that 5, and I have some terms here, and then we added straight down, out comes out a 0. The remainder is a 0 when you did synthetic division. That's because when you plug in a 5, the y value is 0 right here. The y value is 0. F of 5 is 0. So we call that k. And so if you want to think about it, that means x equals to 5 is a 0. But if you want to move that 5 over, I get x minus 5 equals to 0. Now that I wrote it like that, this is a factor. Like when you're factoring a quadratic. I'll make one up here. If this is 2, and this is a negative 2, and I have this beautiful upside down parabola, then x minus 2 and x plus 2 could be a factor. But since it's upside down, there's probably a number in front, like a -1 or something. So we put an A, but just for that doesn't really affect the factor, because even if there was like a negative out front of the whole thing to make it upside down, if you divide everything by A, it goes away anyway. So really the only factors I have is x minus 2 and x plus 2, x squared minus 4. But that tells you that, let's see, x squared minus, there might have been a number in front, like the original polynomial could have been negative x squared plus 4. And if I factor out that negative x squared minus 4 is what I have here. So my point is this: you can take your k and do x minus that k to come up with a factor. So right here, he said we're going to check for a negative x minus 1. He wants to check to see if that's a factor. If that's a factor, then this ought to be true. Okay, and if that's true, then x equals to 1 must have been my x value of a 1 is where this thing probably had to cross through at a 1 if x minus 1 is a factor. So he's asking us to check it. Well, how would I check to see if x equals to 1 gives you f of 1 equals to 0? How would I check for that? I would use synthetic division. It's the fastest way. Oh, I beat you this time. Normally you're way ahead of me, like 5 miles ahead, but you're right. So what I'm going to do, I'm going to do my 2 coefficient, my 3 coefficient. I'm missing 1. There's a 4 and a 2, so I'm missing the third power. So there must be a 0. Sometimes I forget those zeros. I don't know about you. Sometimes I forget them. If I have a 4 to a 2, there must have been a 0x to the third power. So I need to make sure I put a 0 here. Now I put my 3. Then after 2 is a 1, so I'm to minus 5. And then there's my constant with no power. That's the same thing as 7x to the 0. That's very important. So that's going to be a 7. I divide out using synthetic division x equals to 1. And how will I know if it is? What should be the answer right here? The final thing here should be a 0. That's the question. Yeah, that's the secret right here. If that's a 0, I'm good to go. So here goes. This ought to review you guys who was doing synthetic division. 2, 1 times 2, 0 plus 2, 1 times 2, 3 plus 2, 1 times 5, negative 5 plus 5 is 0, 1 times 0, 0. Oh, I don't think it is. Unless I did the math wrong. I'll give it a second for you smart people to take a look at it, because what'd you say?
It's not a 0.
It's not a 0. You agree with my work? Bummer.
Yeah.
Because what I really got here was a 7. So that means it's not a factor. You got a 7 too? Okay, so let's do the other one. He wants to check for the same k, I think. X minus 1 is a factor. Again, if x minus 1 is a factor, that means x minus 1 equals to 0. That means x has to be a 1, if it's true. So I'm going to do it again here. Here goes. A 3, that's a 5th power. A negative 2 is a 4th power. A 1 is a 3rd power. A negative 8 is a 2nd power. 5 is the 1st power. And a 1 goes to the 0 power. I'm dividing out x equals to 1. And when I'm crossing my fingers, and I'm hoping that I get a 0 here. That's what I want. I want a 0 here to say yes. Okay, so here goes. 3, multiply, 3 goes up, add. You just add straight down, multiply again, 1. Add straight down, multiply again, add straight down. I'm getting bored. Multiply again, add straight down. 1 times a negative 1 is a negative 1. Ah, perfect. This one was no. This one is yes. It's as simple as that to test a factor. Okay. Factoring a polynomial with a given zero. This time he's saying, I want you to factor this whole thing. What? When do we factor cubics? We don't factor cubics too often. The reason we don't is because they're hard to factor. So, I'm hoping I can get this one to work for me, but there's really no guarantee. So I'm just going to try it. Let's see. He said, at least he's telling me that one of the zeros is a -3. He's guaranteeing it works. Well, look what happens when we divide by x equals to a -3. If he said x minus 3 is a 0, that means x equals a -3. That means x plus 3 is a factor. That is a factor. So I gotta keep that in mind. If that's a factor, I'm going to do my synthetic division. 6, 19, 2, -3. I don't have any missing zeros. And he said for a fact that a -3 is a 0. So I should get a 0 right here. It should work out because he told me it is, okay? So 6, -18, 1, -3, -1, +3, and sure enough, 0. But you're asking me, why did I do that work if I already knew it was the answer? When you know that one thing is already a factor, that means the leftovers is a reduced polynomial. It means once I factored out the x plus 3, you have another polynomial next to it. That this factor times the remainder will be my original 6x cubed plus 19x squared plus 2x minus 3. You know that x plus 3 times some other polynomial has to be the whole thing. So what do? Is we take this remainder here, and if this was a third degree polynomial, my leftovers is a second degree. It's always one less because you already pulled out one of the x's. So really what I have is x plus 3 times 6x squared plus x minus 1 is the original polynomial. Now he wants me to factor the whole thing. But see, he only gave us one factor, x plus 3. But now that I pulled out the x plus 3 and come up with the 6x squared plus x minus 1, I'll bet you most of you can factor that quadratic in your head. I bet you can factor this in your head. Let's see. What would that be? The x plus 3 is still part of the answer, but I just want to factor this piece. Anybody have any guesses? Or do I got to do it my way? You know, the first number has to be a 6 or a 1, or a 6 and a 1, or a 3 and a 2. And you want to add up to a positive 1 here, and you want to multiply them to get a -1. So I know one of the answers is 3x and the other is 2x. It has to be. So you got to ask yourself, how do I get a -1? One of these must be a positive, one must be a negative. The question is, will this work? 6x squared minus 3x plus 2x? That doesn't work, does it? What must I do? Reverse the signs. This time I just did it by guessing, because I didn't want to. Yeah, I'm just going to say it has to be that way then. Let's see. 6x squared positive 3x minus 2x is a positive 1. A -1 times a positive 1 is a -1. So there they are. There's your three factors. And when you multiply them all together, it should give you this cubic, this third degree polynomial. I'm not really excited of doing more work. since people have come in the room since I've started the lecture, make sure all of you post in chat that you're here. Everybody should post in chat. That way I can double check in case I marked you absent and you really did show up. Okay, so every one of you should put your name in chat. All right, that one's done, I hope. I hope my geniuses in the class agree with this answer. Because, you know, I'm only human. You prick me, I bleed. You pull my hair, I cry. I make mistakes. Example 3. Okay, he's doing the rational zero theorem. Rational zeros theorem. But this is kind of interesting. If you have a polynomial, and I'm going to call this number a q, and I'm going to say this is my highest power. And then I have some other terms all the way till I get to my last term that has x to the 0 power. That's a constant term. I'm going to give that number a p. And the number in front of my highest term, I'm going to give a q. Those two numbers are very important. The reason we call this the rational theorem is because someone just popped in the room. It took me a long time. If you just came in the room, please put your name in chat so I know who you are. If you make fractions, well, actually, I shouldn't even say it's p. P is not really a p. It stands for a number that we use as p. It's the factors of p that I care about. Factors of p over the factors of q. Actually, the factors themselves are different p's and different q's. I'm just trying to make this understandable to us all. We look at those two numbers and we say my possible zeros are always going to be the factors of p plus or minus over the factors of q. And I don't have to do plus or minus again, because if I do plus or minus again, then what happens is it just can't, it's repetitive, because a plus p over a negative q is identical to a negative p over a positive q. So we tend only to say plus or minus p's over q's. Okay, now I got to figure out how he's filling this out. If p over q is a rational number, which means fraction, written in lowest terms, and if p over q is a zero of f, a polynomial function with integer coefficients, that's important. All my coefficients, they have to be integers, not fractions. Then p is the factor of the, I'm going to say, constant term. Constant term, which I said that a minute ago. It's the factors of the constant term, because x to the 0 stands for 1. And then it says, then q is a factor of the, that would be called leading coefficient. Don't you love it how they get complicated? I'd rather just show you how to do the problem, but he wants us to, I mean, it is important as you become a mathematician. Some of you guys will be, because of the programs you'll be in college. Some of you will get enough math credits to actually qualify to teach mathematics in the high school. Allison, see me at 3:15. Okay, so list all possible rational zeros. This means possible. It doesn't mean they are. So you look at this number here, it's a 2. The factors of a 2 give me a plus or minus 2 or a plus or minus 1. Those are the only factors of 2. And then this number here, 6, I'm not going to do plus or minuses now, because I just did my plus or minuses with this one. So I'm just going to say a 6, a 1, a 2, and a 3. So those are my factors of 6. These are my factors of 2 with the plus or minus. So now if I start listing all my plus or minus p's over q's, I start listing them. Okay, here goes. I could have a 2, over a 6. I could have a negative 2 over 6. And then I can reduce them if I want, and I probably will afterwards. That's 2 of them. Then I could have a 1 over 6 and a negative 1 over 6. Those don't reduce. That just took care of that one. I start over again. Plus or minus 2 over 1. That's 2 over 1, and a negative 2 over 1. Well, that just turns into a negative 2 and a positive 2. Then I have my 1 over 6. 1 over 1, or a negative 1 over 1. So now those are all done. Now I'm on the 2. I could have I'm going to continue on this side here. I could have a plus or minus 2 over 6. We did that one already. 2 over 2. That's plus 2 over 2, or a negative 2 over 2. You'll see those repeated. The negative 1 and positive 1 is over here somewhere. I think I did it somewhere there. So I'm done with the, let's see, the 2. Now I do the 1. 1 over 2, negative 1 over 2. Now the 2's are done. Now I got my 3's. I have a 2 over 3, negative 2 over 3. Or I have a 1 over 3 and a negative 1 over 3. Once you reduce all those and cancel out any repeats, you would have to list them. It's a whole bunch, isn't there? I'm not even going to finish it up. I want you to clean it up. 2 over 6 stood for 1/3, didn't it? Didn't I create a 1/3 over there somewhere else? Yeah, here's a positive 1/3 over here and a negative 1/3. So these actually, I don't have to worry about them. 1 over 6, those didn't come up anywhere else, so I'll keep those. 2 over 2 is actually a 1. So I have a 1 right here, if you think about it. That's really a 1. So that one's a repeat. And then negative 2 over 1. Well, I already have a negative 2 over 1 somewhere. No, I don't. That's my only 2 over 1, so I'll keep it. 1 over 1 minus 1 over 1. I keep those two. 2 over 2 and a negative. Those are already used up, aren't they? 2 over 2 is a 1. I already have that. Negative 1. I already have that. Okay, so you keep deleting the extras that are repeated. The point is now, what do I do with all those? Because those only told me, those were my possible zeros. Find all rational zeros and factor f of x into linear factors. So f of x was 6x to the 4. And this is why it takes a long time. Because if you don't use your calculator, you're going to have to guess plus 2. So you're going to start doing some synthetic division. 6, 7, negative 12, negative 3, and a 2. And you have to decide which of those that I did not cross off will I attempt to try to find. Remember, there's 4 possible zeros here. There's 4 possible real zeros. My advice to you is start with the easy ones, like 2 over 1. The factor, so we have 2. So there's no magic, guys. There's no secret. Which ones do I try? I don't really know. If I cheated, use my calculator, I could probably guess a couple of them. But I'm just going to show you what real people have to do. I'll try it too. 6, 12, 19, 38, 26, 52. It's not looking good, is it? 49, 98. No, it's not looking good. So that one didn't work. So I'm going to try the negative 2. Because there is no secret, guys. It's called sweat, blood, and tears. Unless you cheat and use your calculator to help find some. Now, as I do with a negative 2, I want you to grab one of the others that we could possibly use to see which one will work. If I were you, I would probably grab the plus or minus 1 over 1. That's a good one to try. Maybe even a half might be a good one, or a negative half. So pick one and try to beat me to the punch. Try to find one before I can, because I'm not playing a game. There's no magic. It's just hard work. Okay, now some of you guys are just going to sit there and wait for me to get lucky and find one, or you'll wait for another student who works ahead and says, I'm going to try to see if I can find it. But it's a guessing game. Okay, so let me finish up this one here. I'm doing the -2. Let's see if it works. 6, -12. That's a -5. Be careful of your negatives. If you mess up on one sign, you may have lost the 0 that you had. 10, -2, 4. Oh my gosh. I got lucky. -2. Bingo. I won. I found one of the factors. X plus 2 has to be a factor.
One also worked.
And you already did it? Okay, so what I'm going to show you what to do, since Sondos helped me out. What you can do, Sondos, I don't know if you realize this, once we have one or the other, you can start brand new with the reduced set. And what happens is, by starting with the reduced set, you obviously know that now your factors are factors of 1 over the factors of 6. They got smaller. So you already told me 1 works. So I should be able to use a 1 on the new set. What most people do is they do this. Okay, I found 1, so now I'm just going to do a 1 right here and see what happens. And just, you're trying new ones. I tried the -2 and the +2, and I found 1. So Sondos found the 1. So look what happens. I'll do it here first. 6, 6, 1, 1, -1, -1. See, it did work. So we know for a fact that x minus 1 is a factor. Now I'm going to show you something. I'm going to do it again just because I want to show you something. 6, 6, 1, 1, -1, 0. The remainder now, since this started out as a 4th degree and this is a 3rd degree, this must be a 2nd degree. 6x squared plus x minus 1 is your new polynomial. I bet you any money there are people in this class who could factor that by hand. Anybody want to take a guess what it could be? I think we've done this one already. Remember,
we just did this one.
We did it, right? He threw the same polynomial in here just to make our lives easier. Thank you very much, author. I appreciate it when they do something nice. So it was 2x and a 3x, and it had to be -1 and a +1 here. I think that was it, right? 6x squared, 3x minus 2. Yeah, there it is. So there's my other 2 factors. So I got to put it with the other 2. Sondos found x minus 1. I found x plus 2. This equaled to our original f of x. Okay? Now, if you look at the other 2, I did tell you guys, I said, why don't somebody try a 1, somebody try a -1, somebody try a half. Look at 2x plus 1 equal to 0 would have been x equals to a -half. If you'd have tried a -half, you would have won the prize. Or if you'd have tried 3x minus 1 is 0, x equals to a 1/3. If you'd have tried the 1/3, you would have won a prize. But I'll be honest with you, those aren't the first ones I try. I'm too lazy. They're harder to try the 1/2 and the 1/3. Did anybody try a half or a -half? Nobody tried it? Okay. Well, I appreciate Sondos for getting the other one because of mine and Sondos, we reduced this to a quadratic, which you can factor it or you can use quadratic formula. Okay? That was a lot of work. All right. Number of zeros. There actually is a theorem called the fundamental theorem of algebra. And I know what you're thinking. Oh, but we're not algebra. We're in pre-calculus and college algebra. Yeah, but this fundamental theorem of algebra has to do with how to find my zeros, because that's what algebra was for, how to find our solutions. Every function defined by a polynomial of degree 1 or more has at least one complex zero. What does that mean, one complex zero? A plus bi. X equals to a plus bi. Even if b is equal to 0. If b is equal to 0, then it turns out to be x equals to a. Duh. Which that's what we just did right now. We found a whole bunch of a's. Those are my zeros. But if b is not 0, it is possible that x could equal to a 2 plus 3i, which means you will never find this in the picture, because you can't find it. It doesn't cross the x-axis. This is imaginary, the 2 plus 3i. But it is possible that that could be one of your zeros, even if it's not a real number. So they're just telling you every polynomial has at least one complex. Could be imaginary, could be real, could be a couple of each. Number of zeros theorem. A function defined by a polynomial of degree n, that's the highest power, has at most n distinct zeros. A cubic has 3. A fourth degree has 4, like we just showed you. A quadratic is degree 2. It has 2 zeros. Sometimes those zeros are not real. Remember, we talked about the parabola that never crosses the x-axis. It still has 2 zeros. You just have to use the quadratic formula and find out that b squared minus 4ac was a negative number, which meant you have a square root of a negative number. So now that we understand how many zeros I always must have, he says, find a polynomial function f of x of degree 3. So that means he's starting out with some number degree 3. And it has real coefficients that satisfies the given conditions. Let's see. He says the zeros are, here's one of them, here's one of them, here's one of them. Well, he gave me all 3. Why is he giving me this? Because remember when I shared with you earlier that if x minus 1, x equals a negative 1, then x plus 1 must be a factor, right? So I got x plus 1, I have x minus 2, and I have x minus 4 is equal to my polynomial. But there could be a negative something factored out, or it could be a positive number factored out, who knows? So what we do is we say, these 3 terms still could have a number out front. So knowing this, if I know for a fact that f of 1 is 3, then f of 1 would mean this. A times 1 plus 1, 1 minus 2, 1 minus 4 has to equal to 3, because f of 1 equals to 3. The reason I need this, I need to always find out what the leading number could have been that was factored out. So if I know that x is a 1, I'm going to get a y value of a 3, then I take my factors that equaled my polynomial here with the a in front, and I'm going to solve this. So this looks like 3 equals to an a times a 2 times a negative 1 times a negative 3. That means 3 equals to, negative 6, positive 6a, I think. Correct me if I'm wrong. That means a must be a half. So he wants me to find the whole polynomial. So here goes. It's going to be hard. 1/2 times x plus 1 times x minus 2 times x minus 4 is my polynomial. There's f of x. He wants you to multiply this all out and give what the answer is. So I'm going to leave the 1/2. I'm going to multiply these two. Feel free to help me out. X plus 1 times x minus 2 is x squared minus 3x minus 2. Then I have to multiply by this x minus 4. So I'm still leaving the half out. Okay, now this is harder. Please double check my work. I got my 1/2 times x squared times x is x cubed. X squared times a negative 4 is negative 4x squared. Negative 3x times x is a negative 3x squared. Negative 3x times a negative 4 is a positive 12x. Negative 2 times x is a negative 2x. Negative 2 times 4 is, a negative 4. Hope I did negative 4 every time. I hope I did. Is a positive 8. Did I do those right?
Yeah.
Okay. So then this is my function. That's still my f of x. I now need to merge in the half. So 1/2 x cubed. 1/2 of 4 would be a negative 2x squared. That gives me a negative 3/2. Oh, that's cubed. I'm sorry. Cubed. Wait. Oh, these two can add together, can't they? Let me erase that work. Combine like terms is always a good rule. 1/2. I have the x cubed, negative 4x squared, minus 3 squared is a negative 7x squared. These two go together. This 2x and minus 2x would cancel if I did it right. Then I have a plus 8. Okay. It's better to simplify.
Sure, they don't,
Go
they
ahead.
don't cancel. It's 12x minus 2x.
Oh, it's a 12. Oh, it's a 12. I didn't see my writing. Okay, so what does that become? 10x? Thank you for reading my handwriting. All right, so now I got half of each of those terms. X cubed over 2 minus 7 over 2x squared plus 10 over 2 is plus 5x. 4 over 2 is plus 4. There's my polynomial. Of course, if I did it right. Never any guarantees. But I have sondos. And others too. I know you're out there. You're just tired. B. What if negative 2 is a 0, but it's a multiplicity of 3? It means there's 3 zeros of that. That looks like this. Let me show you what B looks like. Let me get this out of the way. Boom, boom, boom. Okay. That means x plus 2 times x plus 2 times x plus 2. If x equals a negative 2, then x plus 2 equals to 0 must be a factor. But he said multiplicity of 3. And then there's always this mysterious a in front that I don't know, and equals to f of x. But he's telling me right now that when x is a negative 1, the y is it a 4? So a times negative 1 plus 2 times negative 1 plus 2 times negative 1 plus 2. Boy, I could have done that better, couldn't I have? Equals f of a negative 1, which all equals to, he says, a 4. We only do that so we can find the a. Okay? So 4 equals to negative 1 plus 2 is a 1. That's a 1. That's a 1. A is 4. So my polynomial must be a 4 times an x plus 2. Well, there's 3 of them. And I'm only listing 3 of them because I have to multiply them out. I wish you would do it instead of me, but 4 times, what did I put a 3 for? Because I'm thinking of the number 3. There was 3 of them. X plus 2 times x plus 2 is x squared plus 4x plus 4. Now I still have to multiply it by another x plus 2. 4 times, I'm just going to do it. You're not helping me, so x cubed plus 2x squared plus 4x squared plus 8x, last I'm on the 4 now, plus 4x plus 8. Combine like terms for, let's see, I have only the x cubed. I have 2x squares plus 4x squares, that's 6x squares. I have 8x plus 4x, that's 12x. Then I have my plus 8 equals to f of x. And if I multiply in by a 4, the real polynomial is 4x cubed plus 24x squared plus 48x plus 32 is my polynomial function. I told you this was a lot of work. And I could probably make 10 mistakes a minute. It's just a lot. You just need to practice a lot of them. I'm not going to get any further, so I'm going to call it right here. We're going to pick up with the conjugate. Oh, yeah, this is tough anyway. The conjugate zero theorem. We'll pick up with that on when? You got two complex Thursday. Numbers, C and D. If you want to take the sum of the whole thing as a complex number, it's the same thing as if I want to take C and add it to D. It's the same thing as just taking C plus D and adding them together, adding this to this and calling the new answer complex. What does it mean in English? If you add two complex numbers together, it's always going to be complex. Well, that makes sense. Even if I'm adding 5 plus 2, those are two complex numbers with 0i. I added up 7 is still a complex number. And then here he says, same thing for the product. If you multiply two complex numbers, like 2 plus 3i times 6 minus 4i, magically, the answer is complex. It still could be complex. Even if your answer came out to a number 10, which can happen, that's still complex because 10 plus 0i is still in the complex plane. All real numbers are in the complex plane. Not all complex numbers are real. Okay? They might have real components. Same thing about a complex number to a power. It's the same thing as that complex to a power, then call it complex, or take the complex number to that power. He doesn't even have us practice any problems. I just think he wanted you to see that there is a properties of conjugates in case you ever have to use them. But there is a conjugate zero theorem. This is important. Whenever you see theorem, it's something that's going to probably be involved as a truth. Like in geometry, you did some theorems, a lot of theorems. If f of x defines a polynomial function having only, this is the important, this has to be true. If this isn't true, the theorem doesn't work. That all your coefficients have to be real. So if I have a complex number, p of x equals to x to the fifth minus 2x cubed plus x minus 10, all these coefficients are real. That one's a 1. This one's a negative 2. This is another 1. This is a minus 10. So this is only true if all your coefficients are real. I know what you're thinking, though, but you should have seen some, well, you didn't do my math lab yet. It is possible to write a polynomial that looks the same, x to the 5, but instead of writing a 2, I write minus 6 plus 4i x cubed plus the x minus the 10. This is a polynomial. It's just not one that normal people look at. It's not, it doesn't look, it looks weird. we're used to this. So this theorem doesn't apply, it does not apply to this polynomial. It applies to a normal polynomial that you're used to seeing. Conjugate root theorem says that if all your coefficients are real numbers, and you know for a fact that z stands for a complex number, equals a plus bi is a 0. Okay, so if you know for a fact that one of your zeros is 2 plus 3i, then you know for a fact, you know that maybe somebody told you this. Maybe I told you this. Maybe I told you that this is a 0 for this polynomial. Which I don't know, I'm making it up, so I don't know. Because these are all real coefficients, you have one more answer for zeros. You know that x also is equal to the 2 minus 3i. Do you remember that term conjugate meant this plus and this minus? Those are conjugates. The a's are the same and the b's are the same, but the signs are opposite each other. Those two are conjugates. Also, let me remind you, what does it mean to be a conjugate? If you take a conjugate pair and multiply them together, do you remember what happened in like chapter 1 of our course? Do you remember what happened when you multiplied something by its conjugate? Or I mean like a complex number by its conjugate? You got 2 times 2 is 4. 2 times a negative 3i is negative 6i. 3i times 2 is a positive 6i. 3i times a negative 3i is a negative 9i squared. I squared stands for a negative 1. So that turns into 4. Those two cancel. Plus 9. That was 13. So in this case, I multiplied these two complex numbers together. The answer is still complex, but I lost the i's. That's the beauty of conjugates. But he's telling me in this theorem that if you have one complex number, you'll have its brother or its sister. It's related, okay? That's important, especially if we're going to try to do a problem, which, let me erase all my chicken scratch here so I have room. Not that I have infinite room. I could always make a new page, but okay. Next example. Find a polynomial function, f of x, of the least degree, having only real coefficients. Okay, he has to tell you this so that you could use the conjugate root theorem. We know for a fact that the zeros are a 3. That means x equals to 3 is a 0. And we know that x equals to a 2 plus I is a 0. And so if I have 2 plus I must have its brother. The other 0 would be what? 2 minus I. And I'm not going to add any more zeros because he said I want the least degree. So I'm going to stick with only 3 zeros. Okay? I could add more zeros and have those still be zeros in the problem. He doesn't want a 4th degree, a 5th degree, a 6th degree. He only wants a 3rd degree. If you have 3 zeros, that's probably a 3rd degree is the smallest degree I can have. How will I create it? I know my polynomial, p of x, or if you want to call it f of x, it doesn't matter, has to be equal to, if x equals 3 is a 0, then x minus 3 is a factor. If x equals 2 plus I, then x minus, let me put that 2 plus I in parentheses, has to be a factor. Then if I know that x equals 2 minus I, then x minus, let me put that in parentheses just so you see it, 2 minus I has to be a factor. Now if you want to get rid of those extra parentheses, it's fine, you can do it. Let me zoom in on this part right here. So I still have my x minus 3. This, if you want to get rid of the extra parentheses, go ahead and distribute. That turns into x minus 2 minus an I times the other one. If I distribute this minus, I still have an x minus 2, but instead of a minus I, this is going to give me a plus I. So that's the difference. X minus 2 plus I. And that's what happens when you have a conjugate pair. The factors look the same, except for they have opposite signs in the imaginary part. Okay? So the factors look very similar. So there's my polynomial. I'm very proud of myself because there they are. It's those three factors. But what do I have to do? I have to do what I don't really want to do. I have to multiply all that out. So I do need a lot more room. So I'm going to see if I can remember how to cut something out. Let's see. Okay, that'll work. And then I can make up a new page and paste it there. Oh, maybe I didn't copy it. There it is. Okay. I first got a copy. Wow, I was holding that thing in memory from another page like about a month ago. Edit. I don't want to copy all that. Okay, I'm going to have to quit because I don't even know if anybody's even paying attention. I could almost do anything I want. It's not working. I mean, it's probably working. It's just I don't know we're doing it right. I lost my cut. Oh. Let me cut it again, just for fun. It just didn't work again. Oh well, I'm going to go to the next page. Someone tell me what I have here. That'd be a lot faster. Thanks for your help. A couple of you said something. Okay, that was that problem there. Holy cow. All right, example 6. I'm already tired. Finding all zeros given only one zero. So he says find all the zeros of this polynomial. It's a fourth degree. And I noticed that all the coefficients are real. That's important because look at the zero he gave me. He says x equals 1 minus I is a 0. That's the only zero he gave me. And I need 4 different zeros. There should be 4 of them. They may be duplicated. 2 of them could be the same, but it still would count as 2. So I have to rely on the conjugate root theorem to say that the other x is 1 plus I. Because I noticed that every coefficient was a real number. So all I have so far is I have some polynomial that is added up to 1. Okay, how do I write the factor? Remember, the factor would be move all this to the other side. So what really happens when I say x minus 1 minus I, look what really happens. It becomes x minus 1 and it becomes plus I because both of those are moving to the other side. That moves over, that moves over. Same thing happens when I say x, when I do the x minus 1 plus I. That turns into x minus 1 minus I. These are my factors. So I have 2 of them. I have 2 factors. I have, let me erase that mark here. I have x minus 1 plus I. I have x minus 1 minus I. That's a polynomial. It's not my answer, though. I need to have 4 of them. So what I'm going to do is realize that if I multiply that together, I have part of it. And I say to myself, how am I going to get the other 2? Anybody have a guess? What did you do in the previous lesson? The other part of this? Nobody did it. No one did any the problems that I did with you. You didn't use synthetic division. You didn't write out your coefficients. 1, -7 plus the 18 minus 22 plus 12, and make sure I have a 4th degree, 3rd degree, 2nd degree, 1st degree, and 0 degree. Do you remember what I did when I have a 0? I didn't really have to do all this work right here. I didn't need to set this up because, well, I do need it, and I will need it later, but I need to find the other 2, okay? So what I do is I take the whole polynomial and I divide it by one of these zeros. And he said, I'm going to use the one he gave me, 1 minus I. 1 minus I. That is one of the zeros. Okay. If I do it correctly, I should get a 0 here. Okay, can I have some thumbs up just to see if somebody's there? Because I haven't heard anybody cry, groan at 1. I already expected that person to be here. A 2, a 3, 4, 5, 6. Okay, there's a lot of you there. Okay, I changed my. I thought maybe you guys were all gone, watching Sesame Street or something. Okay, you're here. But you could help me, guys. You know, I get lonely. So there has to be a 0 here. If I divide it by the 1 minus I, which seems so strange to you, but this was in the other problem too. But so I don't know. So I bring down the 1, multiply 1 times 1 minus I. That answer goes here, 1 minus I. So when I add straight down, it's the -7 plus a 1. That turns into a -6. Then I have 0i plus 1i, or I mean minus an I. It's still minus an I. Okay? Does that make sense? It's complicated though. Now I take this is going to be hard. Now I got to take 1 minus I times -6 minus I, and I'll be honest, I don't know what that is in my head. A couple of you in the room could do it. I literally need a whole sheet of paper. So I have to FOIL that thing and see what I get. 1 times a -6 is a -6. 1 times a -I is a -I. Negative I times a -6 is a positive 6I. And what am I missing? Negative I times the -I is a positive I squared, which means a -1. So I have to say that's a -6 minus 1. That's a -7. Negative I plus 6i is plus 5i. If I did it right. So that answer has to go here. Remember, we multiplied this by this, and it goes over here. So I'll line up the 18 with the -7, and I have a plus 5i. If I'm right. Did anybody want a thumbs up if they think I'm right? I'm looking at my computer to see if anybody, no, they're at one person. Okay, I'm going to run with it. If one person says it. 18 minus 7 is an 11 plus 5i. And the only way you will know if I'm right is if you're doing it with me. And then you agree with it. So, okay, oh my gosh. Now I got to do a 1 minus I times 11 plus 5I. So I'm going to go down here. I need more room. 1 minus I times an 11 minus 5I. I wish there was a shortcut. There isn't. 1 times 11 is 11. Negative 5I minus 11I is a negative 16I. And a negative I times a negative 5 is a positive 5, but the I squared makes it negative. So the positive 5 becomes a negative 5. So that turns me 11 minus 5 is 6 minus 16I. Oh, golly. That answer has to go up here. Negative 6 minus 16I. Add straight down. Negative 22 minus 6 is a negative 28. 0I minus negative 16I.
So that's not what I got.
Oh, for this one? Okay.
Yeah.
Thank you. Can you tell me what I might have done wrong here? What did you get?
I got 16 minus 6I.
I have it reversed. And do I have the right thing? 1 minus I times 11 minus 5I?
I have 11 plus 5I.
Oh, it is. Thank you. How come you didn't stop me back there? Okay.
I didn't notice.
I did. I still appreciate what you've done. Okay, that changes things. 11. Then it was a plus 5I minus 11I is a negative 6I. Is that what you said? 5I minus is a negative 6I. And then it's a 5I times a negative 1I. That gives me a negative 5I squared, which is plus 5. It does turn exactly the opposite. 16 minus 6I. ¿Son Okay. 16 minus 6I. Wow, it looks so similar. Weird. 16 minus 6I. Okay. And negative 22 plus 16 is 6, isn't it? Let me erase that too. Say it again. 6?
Negative 6.
Negative 6 minus 6I. Okay. Now I got to take negative 6 minus 6I. Negative 6 minus 6I. Multiply that by the 1 minus the I. What'd you get, Sondos? Save me some time.
Negative 12.
Oh, beautiful. Oh, negative 12. That means, other than my one dumb mistake that Sondos just saved, I do have it as a 0. Oh my gosh. Okay. Now you say, well, good. What did that do? Guess what? Not much. Because all I've done now is turn my polynomial now into a third degree. I still have to take the answer I have here now, which was a 1 minus 6 minus I, then an 11 plus 5I, and the negative 6 minus 6I. I have to divide that by the other 0 that I know to be true. Oh my goodness. In other words, I divided a minute ago by, come on, let's move. 1 minus the I. Now I got to divide by 1 plus I, the remainders. And here's the thing. This is now a third degree. When I get done, I'll have a second degree. The second degree is easily factored. In other words, what I'm telling you up here, when I said this times this plus something, 2 terms, those 2 terms will be quadratic. Because I have 1, 2, 3, 4, take 2 away, that's a second degree. So yeah, it's just ugly. Nobody does this for a living, that's for sure. Except for me, I guess. If I get it right, this ought to become a 0. All right, let's see if we can do this faster now. Bring down the 1. 1 times 1 plus I is 1 plus I. Add straight down, -5. Oh, the i's disappeared. Woohoo! Bingo. That's great. And then -5 times 1 plus I is a -5 minus 5I. And what does that mean? 4 minus 5 is a -1. What happened to the i's? They canceled. They canceled there too. That's really good news.
Sir,
Yes.
11 minus 5 is 6.
Say it again.
11 minus 5
Oh, that's an 11? I thought it was a 4. It's an 11? Okay, 11 minus 5 is 6. Positive 6. Okay. Thank you for reading my writing. Then 6 times 1 plus I is 6 plus I. 6 plus 6I. 0. Now you're saying, oh man, that worked out nice. What does that mean? That means these three terms make up this quadratic. X squared, 1x squared, because there's a 1 here, minus 5x, because there's a minus 5 here, plus a 6. If I'm lucky, this is factorable, and it is. X minus 3, x minus 2. There's my other two factors. All that work. So I have my other zeros I had x minus 1 plus I and x minus 1 minus I. Those are all my factors. Is that all I wanted to know? Find all the zeros? Oh, okay. Never mind. Zeros. We already had these zeros. X was 1 minus I, and the other was 1 plus I. Right? Those are the zeros I have. 1 minus I, 1 plus I. Yeah. The other zeros are x equals to 3, x equals to 2. So there's the zeros that he gave me. One he gave me, and here are the zeros I just found. Was that fun or what?
No.
No, it wasn't. I don't even think a math nerd thinks this is fun. But I think. Here it is. Oh, where did that come from? It didn't work because that's not what I wanted. I wanted to copy x minus 3 times x minus 2 minus I think, wasn't it? And x minus 2 plus an I. Is that right?
Yes.
Okay. That'd have been a lot faster. Which 2 do I want to multiply first? I don't know if it really matters. It's just plain ugly. So what I'll do is I'll take x times x minus 2, x times, that gives me x squared minus 2x minus xi. Now I'm going to take the -3 times. That gives me minus 3x plus 6 plus 3i. Okay, so that one's done. So all of that has to be multiplied by x minus 2 plus the I. And if you want to simplify this first, might be nicer that f of x is equal to, I still have the x squared. This minus 2x can pair up with the minus 3x. That gives me a minus 5x. So let me cross those out. Let me cross that out. Then I have a minus 6i. Okay, I don't think it pairs up with anything. Not a 6i, minus xi. Minus xi. Then I have, oh, I know, I was thinking plus. I have a plus 6. That's not, and then I have a plus 3i. Okay. I think I've used all the terms. Times x minus 2 plus I. Oh my gosh. Well, you know what? I was thinking that I didn't have a whole lot to do. I guess I'm wrong. It takes a lot of time to do this. And so, oh well, here goes. X squared times x is x cubed. x squared times a negative 2 is a negative 2x squared. X squared times I is an x squared I. I don't like that. Let's see, I hope it disappears. Can I do the 5? Negative 5x times x is a negative 5x squared. Negative 5x times a negative 2 is a positive 10x. Please catch any mistakes, please. Negative 5 times I is a negative 5i. Oh, negative 5x I. Still not done. You know what I'm going to do with the next ones? Let's see. I'm going to line them up like negative xi times an x. Do I have any x squared i's? I do. Use a different color. This one and this one gives me a negative x squared I. So negative x squared I I'll put right here. Then this negative xi times a negative 2 becomes a positive 2xi. Positive 2, no, it doesn't go there. Positive 2xi. What did I have over here? That was a 5, wasn't it? Was that a 5xi? Negative 5xi? Yeah, I think it was. So those line up. Okay, then I have a negative xi times I. I don't have nothing in there that looks, oh yes I do. That is a negative xi squared. I don't have nothing. Negative xi squared. Okay, I've got that done 3 times. So let's go to the next one. 6 times x is 6x. I'll put that here, line it up. 6 times a negative 2 is a negative 12. That lines up with I had a number somewhere. I don't see it now. Maybe I don't. Didn't have a number. Negative 12. 6 times I is a 6i. Do I have any just plain I? I don't. Plus, is it plus 6i? Yes. Okay, last but not least, and I hope I get this right because there's just so many places to get wrong. 3i times x is a 3xi. Do I have any xi's? Right here, 3xi. Oh, 3xi. 3i times a negative 2 is a negative 6i. Negative 6i. 3i times I is a 3i squared. I had I squared somewhere. 3i squared, where? Oh, I do have an xi squared, but I don't have an I squared. I guess not. 3i squared. Okay. I think I have all the terms. So what I'm going to do is put a line here and try to simplify this thing. There are no other x cubes, so that I'm safe. Are there any other plain x squares? I don't see any other, at this point, I don't see any other x squares, so minus 2x squares. What happens to the x squared I minus x squared I? I think they cancel. Oh, I found another squared. I'll bring it down. Minus, nobody told me anything. I have this one here that does go with that, so I'll get these in a second. I have a 10x and a 6x, that's a 16x. I have a minus 5xi plus 2xi plus 3xi. Those two cancel out this up here. These all cancel out. I have a negative xi squared, but don't be afraid. That I squared means negative 1. That just becomes a plus x. I still have that minus 12, not bothering anybody. I have a 6i minus 6i. That's gone. I have a 3i squared, which really turns into a negative 3. Now, look what I have. The good news is I think I could be very close to being correct because I don't see any i's left over. So I'm going to try to finish simplifying it. F of x is x cubed minus 7x squared, that's these two, plus 17x, that's those two, minus 15. I'm not going to guarantee it's 100% right because nobody helped me. And there's 1,000 places to make a mistake, if not 1,000,000, you know. I consider that a very hard problem. If I was to put that on a quiz, it'd be one problem for 20 minutes. It almost doesn't seem fair. Okay. Did anybody find any mistakes? If it's correct, then I should go buy a lottery ticket today. All right. The problem of this wasn't enough either, to be honest with you. It takes so much time. Descartes Rule assigned. Descartes Rule assigned, nobody uses this anymore, to be honest with you. Because in the old days, before we had graphing calculators, and you had this polynomial that may look like this when you graphed it, and you're looking for this, you want to find the zeros, these places here, and maybe there's the x-axis, the y-axis right here, and we don't need to, we got a graphing calculator. If I graph it, I can look at the picture and say, oh, look it, I have 3 negative real zeros. 1, 2, 3. Look over here. I have 3 positive real zeros. And that makes a total of 6. And if my polynomial was something to the 8th power, these only added up to 6. So then I have 2 more to get to the 8. Those must be 2 non-real zeros. So we have technology. If we could graph it, we can just count. But back in the old days, like when I was a little kid, we didn't have that. So you might want to know if your zeros are positive or negative. I'm just going to fly through this because I really don't think, well, I guess nobody asked my opinion, but I don't think it's important that you're a pro at Descartes' rule of signs. It's outdated in a way, but it is math theory. So let your function be a polynomial with real coefficients again, and has a non-zero constant. That means the last number in the polynomial, like when I wrote one up here, where did I write it up here? That last number has to be a number. You can't just say plus x and have nothing left. There has to be a number, okay? He says that it's in descending powers. Of course, we always write it descending. The number of positive real zeros of either, let's see, I don't know what he meant by either the number of, oh, okay, there's 2 choices. They equal the number of variations in signs occurring in the coefficients of f of x. Or let's see, if it's equal, it could be less than, or at least, maybe it is. No, I think it's less than the number of variations by a positive even integer. That doesn't make sense. I have to show you, but I'll show you in a second. The number of negative real zeros are either equal to the number of variations in signs occurring in the coefficients of, here's the secret, f of negative x. Or is, again, I think it's still going to be less than. the number of variations. Okay, what does this mean, variations? He told you you had to have a polynomial, and it has to have every term be real numbers, and it has to have a number at the end that is not 0, and it does. This is f of x. This was a positive 1. So positive 1 to a negative 1, or negative 6, is called a variation. It changed signs. So it changed signs. So there's 1. You're basically counting how many times do your coefficients change signs. This one changed signs from negative to positive, so there's a second one. Now it went from positive to positive. That doesn't count. Then I pick back up at positive to negative. There's a third. So Descartes says you could have 3 positive real zeros or less than, what was my word up there? Less than the number of, less than the number of variations by a positive even. So you got to find only the ones were positive. Here's 1 to a negative, that was a 1 to a negative 6 was a change of a positive. So there's 1. That's a negative, doesn't count. This was a positive to a positive. That didn't change. This is a positive to a negative. I think that counts as or 2. Or less than 2 positive real. I have to look that up to if that's exactly, that's the point. You're supposed to count the changes. Now, that's for positive, okay? For negative, you got to look at f of a negative x. So what you do is you actually got to plug in a negative x in there and go negative x to the 4th minus 6 times a negative x to the 3rd plus 8 negative x to the 2nd. Then I got a 2 times a negative x minus the 1. And rewrite that out, see what it looks like. Negative x to the 4th still stays positive because a negative times a negative. And then this stays negative. The negative times it becomes positive 6x cubed. Negative times negative is positive, so it still stays positive 8x squared. This now changes to a negative 2x. And then the minus 1 stays minus 1. So we do the same thing again. From a positive 1 to a positive doesn't count as a change. From a 6 to an 8 doesn't count as a change. 8 to a negative 2 does count as a change. And then negative 2 to a negative does not. So you have your number of real negative zeros is 1 or less than the changes from a positive to a negative. Were there any positives to a negative? The same one. So there's 1. You could have 1 negative real 0. Wow, all that work just to say, okay, I may have 3, and then I have 1 that's negative. Let's be honest. Do you really care? I mean, how does that help you with anything? I guess in the old days, well, I'll tell you why it'll help. In one of the lessons coming up, we're going to actually have to find out all the I did. We already had that. Remember the p's over q's? Plus or minus p's over q's? Like in this problem, you're either going to be a plus 1 over 1 or a minus 1 over 1. Plus or minus 1 over 1. That gives you a plus 1 or a negative 1. So obviously, that's weird. Doesn't help. Never mind, Descartes doesn't help. If you had a whole bunch of possibilities and you already found your 1 negative 0, you wouldn't try the other negatives because you already had the 1. That's if you wanted to use Descartes first. FYI, nobody does. Nobody does. Why would I? I have a calculator. If I really am that desperate, I can look in the calculator and say, here's one, here's one. You know what I'm saying? How much time do I got? Do I got time to go to the next one? Not really. Well, there is 10 minutes. But what I'll do is double check my attendance and let you go, and you can look at the My Math Lab. Yes.
So how do you find, it says find the non-real complex zeros, so which
Well, the complex, I don't, did Descartes mention complex? No.
Well, it asked them in the question it asked them.
Oh, okay. Determine the positive, negative, and non-real. Okay, so you know this was a fourth degree. Okay, good question. It's a fourth degree, and we said there could be 3 positives, or there could be less than 2. But remember, complex comes in pairs. If you have 1, you have 2. If you have 2, then you have to have 4. So if I have 3 positive reals, there's only 1 left. And that can't be complex. Even if I say there's 2 reals that are negative, did I do the negative? No, I had 1 that was negative. 1 that's negative. So that takes away a pair. And so if you say I have either two positives, or I have 3 positives, because down here says there's 1 negative. So in that problem, you can't have any complex, because if both answers came out to 1 and 1, then that could tell you, oh, that stands for 2. That still leaves 2. That could be complex, because complex have to come in conjugate pairs. Yeah, that problem, I guess I didn't talk about the complex. Nobody, I mean, in this case, you wouldn't have any complex, no matter which way. If you say there's 3 positive, you can't have complex. If you say there's only 2 positive, well, then you could have complex, but then I did the negative, and I have at least one negative. So that means I can't have a complex there either, because I only have 1 of those, and I either have 2 or 3. So I've used them all up. I don't know if that answers your question. I wish you could have given more problems. One example to look at Descartes really isn't enough. I don't even know if I gave you any Descartes in the homework, to be honest with you. I don't think I did, because I'm kind of like, I'm prejudiced that I don't want to make you practice something that nobody really uses. You just need to know it's there, that there is a Descartes rule of signs. But again, it's not practical in a sense, because if I say there's 1 negative, well, if you have a -4 as an answer and another -4, that still counts as 1, because they're the same one. That's called a multiplicity. And so that's why I'm so happy that we are in a modern age where, if I really need to know how many are positive, I mean, look at the picture. If this is a 4th degree, I have 2 answers already. You see? So if I'm looking at the picture, that's real, that's real. I'm supposed to have 4. Where do the other 2 come from? In this picture, the other 2 would be a complex pair. I would have 2 real, 1 positive, 1 negative, and that would mean 2 complex. But if I had a similar problem like that, but my thing did this, where it touches the axis and bounces off, this is something you should listen to, guys. When your graph does this, then you have a multiplicity. I have, in this case, I have 2 zeros here that are identical. I have two zeros here that are identical. If this number was a 3 and this number was a 4, then I have x equals to 3, x equals to 3, x equals to 4, x equals to 4. That means it's multiplicity. And since this is a fourth degree, there only is going to be 4, so I've used them all up. Anybody else have another good question? Crickets. Chirp, chirp. All right, well, that's it for me then. You got your My Math Lab, and it'll be due for you on Monday. By the way, next week, you will be tested at the end of the week. I think you don't go to school on Friday, so tests would be Wednesday and Thursday. There will be a test on everything that we've done in chapter 3. So I've got time for probably one more lesson, and that's it. And what else? There will be a Khan Academy set due by sometime Friday. I'll extend it to Friday, unless you want it to be due Thursday midnight, since you don't have school Friday. No opinion?
Friday's good for.
Okay, got one vote. I guess one vote is a majority then. Nobody is going against you. All right, guys, I'll see you on Monday.
Bye, sir.
Bye. And that's it for that lesson.